Okay. Once again, thank you very much for having me here. I'm Vanessa Mercea. I'm a recent graduate from the Technical University of Cluj-Napoca. And in the past 2 years, I've worked on a project related to machine learning enhancements for Sunquake detection, for automated Sunquake detection. For this work, I collaborated with some researchers at High Altitude Observatory in Boulder, Colorado, from my university and from the Astronomical Institute of the Romanian Academy that are listed here and whom I'm very, very thankful to. So without further ado, I think we can begin. I would begin by making a quick introduction on sunquakes and what they are, for those of you that are not familiar. So they are basically perturbations inside the sun that lead to seismic eruptions on the surface. They are sometimes associated to solar flares, not always. And on the photosphere, they can be visualized as circular waves. Although they have been discovered in 1998, they have only recently become a more commonly detected phenomenon. And we could say that they are very rare. They occur about 2 or 3 times per year on average. There are some years when there are more, but on average 2 or 3 per year. Now, up until now, without machine learning, there are several methods that can be used to detect sunquakes, including movie method, time distance, helioseismic holography. The researchers that I worked with used helioseismic holography in particular. But any of these methods are very often time-consuming, laborious. They require hours of just watching videos of these maps. And also they need a trained eye of those very few people in the world that do understand how to detect sunquakes. Moreover, a big limitation with manual detection is that we're not always sure where and when to look. So we know that some sunquakes are associated to solar flares, but not always. So we don't have an exact clue or recipe about where to find them. So with machine learning, we aimed at taking this a step further towards less manual work. We imagined that we could apply these algorithms to each incoming data points in real time to provide ongoing predictions. But for this, we obviously need a lot of compute power and we need to reach a level of trustworthiness. Now, what I will present shows qualitative results, but we still need to work on the quantity. Now, let's talk about data. We worked with solar cycles 23 and 24. So we covered the time period between 1996 and 2011. And as mentioned earlier, we have used the holography method pre-processing. For those of you that are not familiar with this method, it basically relies on Dopplergrams that we download. And then based on lengthy process, we eventually end up with movies consisting of around 255 frames that look like this, with a lot of noisy regions, but also which capture the active region where the magnetic field is very intense. This magnetic field, this active region where the magnetic field is intense is characterized by a darker patch. I don't know if it's very visible right here. So it's this darker patch here. And then on this active region, we should be able to see the sunquake signature when it arises at a certain point in time. And in here, I highlighted it with this green circle. So if we look inside it, we can see that the gradient intensity of a certain portion of pixels keeps increasing and then slowly decreasing back. So this would be a sunquake signature that we aim to detect automatically. Now, this example that I showed was rather simple, easy to grasp. Here is another example. So unless you have a really good resolution or you zoom in or a very good light on your monitor, it should be very difficult to see the sunquake signature in this other example, in this other event from our data sets. So what I want to underline here is that these data sets generally come with a lot of challenges. I would like to highlight this one in particular, the data sets are very, very unbalanced. On average, we have 4% of the total images of the total frames of our events as Sunquake signatures with Sunquake signatures present. And out of those 4%, there are the marginal frames. So like the first, second, and the last frame of the Sunquake are obviously less clear. The signatures are less clear, which makes it quite difficult for machine learning models, which need a lot of data to deal with it. Secondly, the data is quite complex. So each event has a different active region, a different intensity for the Sunquake signature, and we don't have too many events. Overall, I believe we have around 80 something. With our data sets, we also have some fake signals generated from the from the holography preprocessing method. Some of them we got rid of to reduce the noise in our data sets, such as this one. But some others we left. For instance, there are situations where the exact same characteristics of a Sunquake signature are present in the image, in our images, but are not right inside the AR, but rather on the edge, maybe characterized by a vortex-like movement, which are fake signals, but that we wanted to leave there so that our models would learn that they are not correct Sunquake signatures. Now, last but not least, before we started this, we didn't know any other machine learning applications for this data, so there was no guaranteed success back when we started. I will now move on to the approach and briefly describe the process. So we initially started analyzing data. I, at least as a programmer, had to, I'm not a physicist at all, I had to understand the human thought process behind the detection of sunquakes so that I could understand the predictions of my model and judge them. So this is what we started with. Then we constructed the actual data set that is available on Kaggle. So if you would like to check it out and try to solve this problem by yourself, you are welcome. Then, like a year back, we tried some initial attempts. We tried simple architectures like stacking some convolutional neural networks together or implementing reconstruction-based learning methods, but these all deemed insufficient even to converge on these data sets. We eventually ended up trying out contrastive learning techniques that I will present in a moment, which proved to be quite good. And together with the object detection, we managed to predict both the time and the location of a sunquake. Last but not least, we performed an analysis on additional data sets using physics-based validation with the help of our collaborators. So to better underline once again, we want to, one, predict time. So we want to predict, let's say, from frame 57 to frame 64, we have sunquake. And then we want to predict location. For the frames where we know we have a sunquake, we want to know exactly where in the image that sunquake is. So two steps. The first step with predicting time is a pipeline, but a simple pipeline, where we apply first contrastive learning with the purpose of converting the original images, which are two-dimensional, to vector representation, so to a reduced representation, let's say from 224 by 224 to 128 size vector. Over these vectors, we can perform classification using various techniques. This is why we separated this process into two. For the actual classification, so whether an image contains or does not contain a sunquake, we tried linear regression, k-nearest neighbor, SGD, support vector classification. In the following slides, I will focus only on support vector classification with the results to make it easier for the presentation. And then moving on to the location, we have used object detection techniques. Specifically, we use the faster RCNN approach. So the purpose here was to retrieve all regions where a sunquake was detected. So all boxes where the signature is present. I will briefly now describe the each of these three sub-steps in the pipeline, beginning with contrastive learning, which is divided into two parts. Unsupervised contrastive learning and supervised. So first, with unsupervised contrastive learning, our goal here by applying these techniques is that of trying to learn patterns from the data. So with unsupervised, we completely ignore the fact that some images in our data set are positive or are negative, or so contain a sunquake or don't contain a sunquake, but instead try to focus on learning patterns, learning the structure of the AR, learning where the noise is, and so on. And to do this, what we do is we take any image in our data set, or each image in our data set, we apply a set of transformations to it. So you see random erasing or increasing intensity or blurring and so on. And then we try to minimize the distance between the resulting vector after applying the convolutional neural networks, the resulting vector of the original image and the resulting vector of the augmented image. And by that, we force the model to pay attention to the variously transformed areas of the image. And again, in this way, we learn patterns from the data. Then, after having learned some patterns from the data, on top of this, we stack a supervised contrastive learning, which is quite similar from what I just mentioned with unsupervised. But in this case, we do care about whether an image is a sunquake, so presents a sunquake signature or not. And to enforce that, to learn the time occurrence, to enforce the signature presence in the embedding vectors, what we do, instead of only trying to minimize the distance between the resulting vector associated to each image and its augmentation, we also try to minimize the distance between each image and all other images that are of the same class. So all other positives. Now, after having done this, sorry, I missed one slide. When doing this, we have used a series of custom transformations that seem to be very, very useful for our model convergence. If we went the straight way with general augmentations typically used in machine learning, nothing worked as expected. After introducing our domain-specific augmentations, things started to finally work out. So, of course, we did the geometric transforms, which are typical rotation strips and so on. We did the solarized low-pass filter to enhance signals. So here we have an example of how this works. We have the original images on the top, and on the bottom we have the transformed version. So what this transform basically does, it's a low-pass filter, so it enhances low frequencies, and we see the sunquake being very highlighted in some scenarios. So this is actually a better capturing of the sunquake, but in some other scenarios we see the noise being highlighted. So because we don't want to make the model believe this is the image it should look to, we only apply this transform randomly to let's say 50% of the images or 50% of the time with a margin. A second transform that we have introduced that has been particularly useful in improving the model's accuracy in terms of marginal sunquake frames, so the transition to where there's no sunquake and there is a sunquake, is this time-based mixing transform. And for this, in the contrastive learning process, instead of only taking one image and converting it to a vector, we instead look at three consecutive images. So we look at frame 74, 75, 76 instead of just frame 75 to better capture these transitions. Lastly, we introduced this transform to force the model to pay attention to various areas of the image without or at least with a low chance of occluding the actual sunquake. So by this, we randomly crop or erase certain parts of our image by adding between 2 and 8 rectangles of various small sizes. There is a really small chance that the sunquake will be occluded. So this is why we had to replace the typical used random crop transform with this random erase. Okay, and then for the second part, where we have the vectors resulting from the contrastive learning, we use, as I was saying, various classifiers, mainly support vector classification, as I was mentioning, we'll see in the results. So with this algorithm, let's imagine we have here the vector representations for the non-Sunquake class, and with red, we have the vector representation for the Sunquake class. We draw a hyperplane between these vectors. Then we try to find the point that is closest to this hyperplane, vector that is closest, which we called support vectors from each class. And then we try to bring these distances between the support vectors and this hyperplane to be equal. It's quite a simple and effective algorithm. We combine this algorithm with SMOTE. You might have heard of this. It's a technique used when we have class imbalance to artificially generate more samples of our data, and we do combine our classification with SMOTE augmentation, our data with SMOTE augmentation beforehand to further increase our positive examples. Okay. For object detection, as I was saying, we are using faster RCNN, a very popular computer vision algorithm recently. So basically, we have the image, we have some convolutional layers that reduce the image to a smaller size. On the smaller size, there is an algorithm or network that performs an algorithm to select in a smart way regions where objects may reside, which are called region proposals. And then there is a classifier on top that takes the resized proposals and classifies them as Sunquake or background. Finally, the regions that are classified as Sunquake are returned to us. This is an example of how the object detection looks like when applied to one event in our data. We see that sometimes the boxes vary in size, but they maintain position. As long as they maintain position for the desired number of frames corresponding to Sunquakes, we accept the results. Now let's move on to the results. We focused on two main models, one that had no external influence and one that did have some external influence. I will start with the one without any influence. This one had metrics that were not so good, but actually, if we looked at the results, we noticed that this model was very, very good at predicting marginal frames. So the transition frame from non-Sunquake to Sunquake and the transition frame from Sunquake to non-Sunquake, the beginning and endings. And for this model, any two samples from one single event, such as frame 1 and frame 2 from one single event, only belonged to only train or only belonged to only tests. So this is why it had no external influence. The pipeline is the one that I described. So unsupervised contrastive learning, supervised contrastive learning, and then classification on top of that. We see that the results with SMOTE are a bit better. If we are to look at the second model, so it's the same step. It's just that the same steps. It's just that the shuffling is done differently. So for this model, if I take frame 1 and frame 2 from the same event, it is possible that frame 1 resides in the test set and frame 2 resides in the training set. This model had good results for all frames, not only marginal, but we did find similarities between the two models, even though trained differently. It is also very good at separating in the vector space, separating marginal Sunquake frames, just like the previous model. Now, after having seen the results, we wanted to analyze what the models do on new data, on unseen data. And for this, we selected some uncertain events, some events that were rather difficult to detect with the naked eye, that the model has not seen before. We applied the pipeline that I just mentioned. We filtered the results such that we only considered for the OD to find the location, we only considered the frames that were predicted positive by the CL. And for the OD, we only considered the results that presented the Sunquake signature in the same spot for at least 6 frames, because otherwise there would be a lot of clutter with Sunquakes that would last for 2 or 3 frames, which is invalid. And lastly, we performed the physical analysis using SDO data. I will show you in the next slide. So we had two events that were uncertain that we wanted to look at. And after having gone through the process that I just explained, we looked in the IA94 channel and time of our CL and OD predictions. And we have found, in this case, a very weak seismic emission. I hope I'm correctly saying this. And in the second case, we looked in the IA304 because, for my understanding, for the second scenario, the seismic emissions were a bit stronger and more evident. But it's nice, we see that they overlap with our predictions quite nicely, for at least for the 6 frames duration that we see here. Okay, let's look back a bit. So you have the timeline here if you want to recap. I will go through the findings. So we found that noise is quite impactful. If we look at the data, even at the beginning, we see that it's quite noisy, and it's very easy to not be able to distinguish the Sunquake signature from noise, even for models. So very, very tricky. Secondly, we found that these types of models are capable of predicting very, very weak sources. We found that custom augmentations, especially the time-based mixing and especially the solarized low pass, were very, very, very impactful on the convergence of our models. We found that the models are rather prone to predicting short duration signals. So Sunquakes that last for three frames, which are incorrect. And we stress that this is related to the fact that when introducing the custom time-based mixing transform, the one that was combining multiple consecutive frames, we only looked at 3 at once. So if we were to look at 6 at once, let's say, that would maybe make a bigger difference. Also, there is some sensitivity in our models towards false signals, especially around the active region if we have some high intensity noise. And lastly, this is finally a good one, a positive one. All of our models were adept of predicting Sunquake margins. So even the ones that have external influence, even the ones that did not have external influence, very good at predicting the transition ever since introducing the time-based mixing transfer. So this was my presentation. Thank you very much for joining. If you have any questions, feel free to ask.